All right, ladies and gentlemen, we're taking a look at section 6.1 today, dealing with power series and their relation to functions. And so we're going to start with the definition of what a power series is. Okay, a power series is of the form of this infinite series. Where n in this case starts at 0, so we go c sub 0, x to the 0, meaning just c sub 0. Then when n is 1, c sub 1, x to the 1. When n is 2, c sub 2, x to the 2. When n is 3, c sub 3, x to the 3, and so on forever. Okay, where in this case the x, of course, is a variable, and these c sub n's are constants. So, give you an example of a power series. X to the n as n goes from 0 to infinity. And this, in fact, turns out to be a very useful and famous power series. This would be when n is 0, x to the 0 is 1. When n is 1, x to the 1. When n is 2, x squared, and so on. So basically it's this form where the constants are 1, okay, in this special case. And what we could notice about this is that the subsequent term is always the previous term times an x. Therefore, this is a geometric series. And that's the reason we're starting with this one, is we know something about this particular series. We know it's geometric, and we can use our information about geometric series to help us better understand this. Okay, the common ratio here, the r in the geometric series is x in this case. And so we know that this converges if the absolute value of x is less than 1, and it diverges if the absolute value of x is bigger than or equal to 1. Okay? And we also know the formula for what this converges to. In other words, when the absolute value of x is less than 1, the sum of this series is 1 over 1 minus the r, which is, of course, x. In other words, this function, 1 over 1 minus x, has a series form like this. Meaning we can represent this function as an infinite power series. And of course that infinite power series is nothing more than a polynomial. Okay, so this starts to get at the idea of why we're interested in series in general and power series specifically. They allow us to take a function and re-represent it as an infinite polynomial. And the reason one might want to do that is polynomials are much easier to work with in calculus than other functions are. We know how to differentiate and integrate polynomials very easily. So think about it. If you can represent functions in general as polynomials and do the calculus on the polynomial version of that function, then you can save yourself having to do some very difficult differentiations or integrations. Okay, so that's the whole gist of the last part of the course right there. We represent functions as polynomials, infinite polynomials, to make the calculus easy to work with them. Okay. All right, now, one thing that is useful is note we can recenter a power series by shifting the series. So think about this. You've got this power series, and we want to shift to center at x equals a. Well, the way we do that is we simply subtract a from the x. now this power series is centered at x equals a. Okay, so let's look at an example of this. You may notice that this is the power series up here, simply shifted so that it's centered at 2 instead of centered at 0. Okay? And so how does that affect this? Well, let's write out a first few terms. When n is 0, that's 1. When n is 1, that's x minus 2. When n is 2, that's x minus 2 squared. When n is 3, x minus 2 cubed, and so on and so forth. Okay? It's the same power series as up here. It's just been shifted now to be centered at 2 instead of at 0. Okay? So what happens is this. Up here, what made this converge was the power of x, or the x that's being raised to a power. That's your r. That being less than 1 in absolute value is what made this converge. Well, this time down here, it's the x minus 2 that is playing the role of the r. In other words, you multiply each term by an x minus 2 to get the next term. So in order for this to converge, that x minus 2 has to be less than 1 in absolute value. Which means, and of course it diverges, when the absolute value of x minus 2 is bigger than or equal to 1. Now this means that x minus 2 is trapped between 1 and negative 1. Which means if you add 2 everywhere, adding 2 here, here, and here, x is between 1 and 3, and this is where it converges. Okay? If x is not on this interval, we do not have convergence. This is called the interval of convergence for the power series. And we're very interested in knowing those intervals of convergence. Okay? Okay. So let's try to summarize what we've just said here in a theorem. Suppose we're given this power series. Then either this series is going to converge only for one value, and that is x equals a. X is not a means diverges. Now if x is a minus a is 0, you just have a 0 here, which means all the terms are 0, so of course it has to converge. Every series will always at least converge at its center. Okay? But what this is saying now is that there is the possibility that's the only value of x for which the series converges. Now, a second possibility is that the series will converge for all values of x. So, second possibility, the series converges for all x, meaning that the interval of convergence is the entire real number line. Now the third possibility is the series converges for the absolute value of x minus a less than some value r, where r is a real number. And we don't use the letter r because r stands for real number. In fact, r is going to be standing for the radius of the interval of convergence, as we'll define in just a minute. Okay? the series diverges. When x minus a is bigger than r, and we don't know what happens from this so far when x minus a equals r in absolute value. So when x minus a equals r, the series may converge or diverge. And that is where we have to do a little bit of work. We would have to figure out for the value that when x minus a in absolute value is equal to r, what happens with the series. Okay? Okay, note again, r is called the radius of convergence of the power series. Why? Because you go r to the right and r to the left of the center of the series to get the interval over which you converge. Okay? All right. So let's look at an example here. So that we can understand for sure what we're talking about when we talk about the interval of convergence and the radius of convergence. Let's go back to our example here of this power series. Okay. And I want to show that this, or we know already, because this is geometric, so it converges for the absolute value of x less than 1, and it diverges for the absolute value of x bigger than or equal to 1. So the interval of convergence comes again from the absolute value of x is less than 1, which means that x is between -1 and 1. And that's your interval of convergence. Okay? The r value here, the radius of convergence, is 1 in this case. Okay? Let's look at a second example here. Suppose you're given f of x is equal to x cubed over 2 minus x. Can we use our knowledge from up here that this series converges, and it converges to 1 over 1 minus x, to figure out how to write this now as a power series? Well, sure. What we do is we rewrite this. We say, okay, that's an x cubed, pull the x cubed out, times 1 over, and now here I'm going to write this as 1 minus x minus 1. And so you'll notice, of course, that the 1 minus of a minus 1 becomes 2. That's a 2 minus x, same as the denominator here, and the x cubed times 1 is an x cubed. Now, what's the benefit of this? Well, this here, the 1 over 1 minus x minus 1 in parentheses, is of this form here, with the center shifted to 1 instead of 0. So all I have to do is take this power series and shift it so the center's at 1 instead of 0, and I have the representation of this part of it. Okay? And of course the x cubed times it completes it. So again, this part right here, using the results from up here, is going to be the series 1 plus x minus 1 plus x minus 1 squared, and on and on. And so there's your power series representation of this. Okay? You simply would multiply this out times all of this. That's a 1 there, sorry. And there's a power series representation for this function as well. Okay. All right, now, what would be the interval of convergence? Well, this is geometric still, and so it's going to converge for this thing here, the r value in the geometric series, less than 1, which means that x minus 1 is between -1 and 1. Now, if you add 1 everywhere here, you get, there's the interval of convergence. Okay. All right. So let's take a look now at, from the exercises, problem number 8. In number 8, they say, suppose that the limit as n goes to infinity of a sub n plus 1 over a sub n is 1. Okay? Find the radius of convergence. And here's the series you're given. Okay. So, looking at this thing, what do I notice is going on here? Well, I can apply the ratio test. And remember, the ratio test says you take the limit as n goes to infinity of the n plus 1 term. So this with every n increased by 1. Divided by the nth term. So divided by this means we go ahead and flip it and we multiply. And now I have to compute this limit. Well, let's break this up. The a sub n here and the a sub n plus 1 here, put those out in front. And then here we have the x to the n plus 1 times 2 to the n over 2 to the n plus 1 and x to the n. Now I already know from the supposition up here that the limit of a sub n plus 1 over a sub n is 1. So I know this part goes to 1. I don't have to worry about that. Now focusing on this part, 2 to the n and 2 to the n plus 1 cancel, leaving just a 2 in the denominator. X to the n and x to the n plus 1 cancel, leaving just an x in the numerator. And so what you get here is this limit is 1. The limit of this is an x over a 2. And in the ratio test, if the ratio's limit is less than 1, we have convergence. So in other words, when the absolute value of x minus 2 is less than 1, we have convergence, which means that x is between 2 and -2, and the radius of convergence on this thing is 2. In other words, when you solve this by multiplying both sides by 2, there's your radius of convergence. Pops right out for you. Okay? All right. Let's take a look at problem number 14, where instead of using these arbitrary forms like they did here with an a sub n, they're going to give you a specific series. So in 14, the series is n is 1. Instead of starting at 0, they start at 1. That's not a problem. The first term never affects whether the series converges or diverges, as long as it doesn't blow up at least. And we want to know what the radius of convergence and the interval of convergence are. So find r and the interval of convergence for this. Again, use the ratio test. So I'm going to take the limit as n goes to infinity of this thing with the n's increased by 1. Divided by this term itself, which means flip it and multiply. And now the cancellations we get here. Of course, well, we're taking the absolute value, so the negative 1 to the n, negative 1 to the n plus 1 make no difference. Those go away. The x to the n cancels with x to the n plus 1, leaving a single x. And so now if I pull out that x, which since it has no effect by the limit, as n goes to infinity, it's the absolute value of x times the limit as n goes to infinity of the square root of n over the square root of n plus 1. And as n goes to infinity, these two look the same, so this limit right here is 1 times the absolute value of x. Okay, so when does this converge? When the ratio's limit is less than 1. So that means r, the radius of convergence, is 1. Okay? Now that means that the interval of convergence looks like this, but what we don't know is when x is negative 1 or when x is 1, do we have convergence or divergence? So now we test each end point of the interval of convergence. In other words, when x is negative 1, what does our series look like? Well, it's negative 1 to the n times negative 1 to the n over the square root of n. These multiply together to make 1. Negative and a negative cancel, don't they? And so tell me, what does this series do? Well, this is a p series with p as a half, so that diverges. And since that diverges, that means when x is equal to negative 1, we have divergence in this interval of convergence. We do not include negative 1 as part of the interval of convergence. What about when x is positive 1 at the other end of the interval? Well, if you put a positive 1 in for the x here, you simply get negative 1 to the n over the square root of n. And that is an alternating series, where the b sub n is 1 over the square root of n. This is positive, decreasing, and the limit goes to 0. In an alternating series, when the positive term is decreasing and goes to 0 in limit, the series converges. And that means when x is positive 1, we do have convergence. So the interval of convergence, we do not include the left endpoint, but we do include the right endpoint. The radius of convergence is 1. The interval of convergence is from negative 1 to 1, not including the negative 1, but including the positive 1. So kind of interesting, isn't it? This is really why we had to learn things like the alternating series test, the integral test, the p-series test, was so that we could figure out for the endpoints whether we had convergence or divergence. Okay? And so really it's a lot of little tests for a very minor thing, which is to know what's happening at the endpoints. As it turns out, you will see then, the ratio test is really the predominant test in all of this. And the other tests are used just to fill in the information about what's happening at the endpoints of the interval that the ratio test gives us. All right, let's try problem number 16 next. In 16, we have the series n is 1 to infinity, n x to the n over e to the n. Okay? So let's apply the ratio test. The limit as n goes to infinity, take these and increase the n by 1. So n plus 1, x to the n plus 1 over e to the n plus 1. And then divide by this, which means flip it and multiply. And now we have some simplification to do, don't we? X to the n cancels n of those, leaving an x. E to the n cancels n of these, just leaving an e. And so you have an x and an e, which are independent of n. You can pull those outside. And what you're left inside with is n plus 1 over n. And n plus 1 over n, as n goes to infinity, just goes to 1. So you're left with absolute value of x over e. And you know, for the interval of convergence, what you have to do is say that absolute value of x over e is less than 1 to make convergence occur. If you multiply both sides of this by e, you can identify the radius of convergence, therefore, to be e. And then the interval, well, there's the form of the interval, right? And now we have to test the endpoints. When x is equal to negative e, what does this series look like? Well, negative e to the n and e to the n cancel each other. And you get this. So what does that look like? When n is 1, when n is 2, when n is 3, n is 4, when n is 5, when n is 6, and so on. Okay? What does this do? Well, this is diverges, and the divergence test is what tells you that. The limit, as n goes to infinity of n times negative 1 to the n, what does this go to in limit? Does not exist. Okay? And since that limit doesn't exist, we do not have convergence here. What about when x is e? Well, then those simply cancel. And you got that. And easily you can see that diverges, right? It's the divergence test again. So the interval of convergence for this does not include the two endpoints. It's the open interval from negative e to e. All right. Let's try problem number 20. And then the next couple, what we're going to really practice with is the idea of how you do the cancellations properly in the ratio test. So in 20, we have x to the n over n factorial. Let's find the radius of convergence and the interval of convergence for this. So use the ratio test. Increase your n by 1. Flip this and multiply to create the division by a sub n term. Simplify. Those cancel. You have an x here. That x is going to come outside. And the way you're going to simplify in here is simply n plus 1 factorial is, of course, n plus 1 times n factorial. And now you can cancel those. Now take the limit as n goes to infinity of 1 over n plus 1, and you get 0. Okay, so what that means is, okay, this value here is always less than 1 for any x. That means that the radius of convergence is infinite, and the interval of convergence is the entire real number line. All right, let's try number 30. They ask us simply to find the radius of convergence for this in 30. And the series is from 1 to infinity of 2 to the 3n power times n factorial cubed over 3n quantity factorial all times x to the n. Okay? So the ratio test is what we use. The limit as n goes to infinity. I take this term now and I bump up the n by 1. Now think about that. When this n increases by 1, it's going to be 3 times the quantity n plus 1, or 3n plus 3 as the new power. When this n increases by 1, it's n plus 1 factorial, now to the third power. When this n increases by 1, just like up here, when n increases by 1, that's 3 times n plus 1 is n plus 3 factorial. Okay? And this x to the n, put it up in the numerator, increase by 1 is that. Now flip this and multiply. 3n factorial in the top, all of this now in the bottom. So 2 to the 3n, n factorial cubed, and x to the n. And do your cancellations. X to the n cancels n of those, leaving an x. That x is independent of n, so bring it outside the limit. And the rest of this, let's see how we go through the arithmetic of canceling. 2 to the 3n plus 2 is 2 to the 3n times 2 to the 3. n plus 1 factorial cubed. Well, n plus 1 factorial is n plus 1 times n factorial. And 3n factorial we leave as it is. Down here, n plus 3 factorial. That's n plus 3. Did I write that right? Let's check it again. Oh, 3n plus 3, right? Because 3n factorial here. 3n plus 3. So 3n plus 3, 3n plus 2, 3n plus 1, and then 3n factorial for all of that. And then the 2 to the 3n and the n factorial being cubed. Now let's go through the cancellations here. 2 to the 3n and 2 to the 3n cancel. 3n factorial cancel. n factorial cubed and n factorial cubed cancel. And so what we're left with is a 2 to the cubed and 8, which is independent of the n's. I can pull that right outside. We have n plus 1 cubed. There's nothing else in the top. We have an n plus 3 and 3n plus 3, a 3n plus 2, and a 3n plus 1 in the bottom. So what does this look like? Well, the highest power on the top is n cubed, and the bottom is 27n cubed. So this part here goes to 1 over 27. And so your limit, 8 over 27 absolute value of x. We need that to be less than 1, which means the absolute value of x is less than 27 over 8, and that means your r is 27 over 8. We found the radius of convergence for this. Okay. All right, just a couple more to get through here. Another one where we practice the cancellations to make sure we understand them well is 32. And from 1 to infinity, we have 2n factorial over n to the 2n times x to the n. So the ratio test. You take the limit as n goes to infinity of this with the n's increased by 1. So when you increase this n by 1, that's 2 times n plus 1, or 2n plus 2. There's x to the n. You increase that by 1. You increase this n by 1 and this n by 1, so you get n plus 1 to the 2n plus 2. Now multiply that by the flip of this. And do your cancellations. Well, first, the x's are always easy. X to the n cancels with n of those, leaving an absolute value of x, which you can pull outside the limit. 2n plus 2 factorial is 2n plus 2 times 2n plus 1 times 2n, and that's where I'll stop and write a factorial so that I can have it cancel with this one. N to the 2n, and in the bottom, n plus 1 to the 2n, and n plus 1 to the 2. And there's your 2n factorial. Now, cancellation, 2n factorial and 2n factorial. Now, what happens as n goes to infinity? Well, you've got a 2n times a 2n. Okay, so that's a 4n squared times n to the 2n. Let's write that out just to make sure it's clear for everyone. Two n times 2n times n to the 2n. The plus 2 and the plus 1, they make no difference as n goes to infinity. Just like down here, the plus 1s make no difference as n goes to infinity. So in the bottom, n to the 2n and n squared. Now, n to the 2n cancels, n squared cancels, and you've got just the 4 there. Okay, so there's your limit. And we know that when this is less than 1, we have convergence, which means absolute value of x has to be less than a fourth, which means that the radius of convergence is a fourth. All right. On the next two, use the fact that 1 over 1 minus x is this sum. With that interval of convergence from -1 to 1, to rewrite the power series given to you. In 36, the power series you're given, or the function you're given, is 1 over 1 plus x squared. And of course that's centered at 0. I want to use this up here to write this as a power series. So the way I do that is I think of this as 1 over 1 minus x squared. Now it's matching up with this, where playing the role of x is x squared. So over here, all I have to do is replace the x with x squared, and I'm done. There's the power series representation for this. And the interval of convergence for this thing, well, now it's x squared has to be between -1 and 1, which means x still has to be between -1 and 1. And finally, last example, number 40. F of x in 40 is 1 over 1 minus 4x squared. And this again is centered at 0. Now playing the role of x is 4x squared. So that's going to be this as the power series. Okay, and this is going to converge for 4x squared less than 1, which means x squared is less than 4 in absolute value, which means that x is between -2 and 2 for the interval of convergence. Okay. All right, so I think you can see that if you know a formula like this, that can help you to write a bunch of different functions into a power series form. Okay. And so there are a few formulas like this that are worth knowing when it comes to working power series. All right, so give those problems a try in the exercises, see how you do. As always, if you have any questions or concerns, don't hesitate to contact me.